During the development stage of an engine, or more specifically the engine's compressor, a graph will be plotted using data which includes the maximum compression ratio and maximum air mass flow that the engine is capable of sustaining at a particular RPM. A line is drawn which connects points on the graph which equate to the maximum compression ratio and maximum air mass flow at a number of different RPMs. This line is called the surge-stall line. Engine operation at compression ratios or mass airflow values above this line will promote compressor stall and surge. A line is also drawn connecting points on the graph where the engine is operating at RPMs where the compression ratio and the air mass are proportionally matched. This is called the normal operating line. There is a zone between the stall surge line and the normal operating line which is called the stall margin zone. This zone allows for the compressor efficiency reducing throughout its working life, and the inevitable fluctuations which occur in the atmosphere and in the engine fuel system management. Every compressor has an optimum operating point on the normal operating line, which represents just one particular compression ratio, compressor speed, and air mass flow. The optimum point is called the design point. Ideally, the design point occurs on the graph where the engine will spend most of its service life, that is, at cruising speed at altitude. An engine operating at compression ratios, mass airflows, and RPMs that fall below the normal operating line will be operating below its normal efficiency. For instance, throughout its service life, the compressor efficiency will, for various reasons, including minor blade deterioration and contamination, become lower and lower. This will cause the surge stall line to move closer to the normal operating line, reducing the size of the stall margin zone, and thus reducing the tolerance which was initially allowed for those inevitable fluctuations in the weather and fuel system management. This picture shows the basic methods of construction which are commonly used in compressor assembly. The rotor shaft is supported in bearings and is coupled to the turbine shaft in a manner that will allow minor variations in alignment to be catered for. The centrifugal load imposed on the compressor dictates that the rotor blades are fixed to a disc, which itself is fitted around the rotor shaft. The types of rotor blade fixing methods vary, the most common being that where the root of the blade is shaped to form a dovetail joint and secured to the disc by a pin or locking tab. This picture shows dovetail fixing of the blades in the complete disc, with one loose blade in the foreground which utilizes the fir tree type of fixture. The dovetail method of fixing does not ensure that the blade is held immovable in the disc. In fact, the blades are quite loose until firmly seated by centrifugal force during engine operation. Thus, when the engine is windmilling on the ground, the blades rattle loosely and make a sound which is similar to the noise a bag of nails makes when it's being shaken. It's become more and more difficult on smaller engines to design a practical compressor blade fixing method and, at the same time, maintain minimum rotor disc weight. One way of getting over the problem is to produce rotor blades integral with the disc. This type of blade and disc combination is called a blisk. The stator vanes, similar to the rotor blades, are also airfoil-shaped. They are either fixed into stator vane retaining rings, which are themselves fastened to the casing, or they are fixed to the compressor casing directly, as are these shrouded vanes shown here. The shrouding at the inner ends of the stator vanes prevents them vibrating. The vibration can be induced by the velocity of the airflow over them. At the low-pressure end of the compressor, the casing is constructed of aluminium alloy. Further down the compressor, The intermediate casing is manufactured from steel alloys. Around the high-pressure section of the compressor, the temperature of the air is so high that nickel-based alloys are the only materials capable of withstanding it. The rotor blades are of airfoil section and are normally made from nickel alloys. They are machined to a close tolerance before being attached to the rotor disc. The rotor blades reduce in size from the front to the rear of the compressor to accommodate the convergent shape of the air annulus, as shown here. Some of the low-pressure stages of the compressor, where the temperature of compression is not too high, may have their rotor blades manufactured from titanium. Indeed, as higher temperature titanium alloys are produced, these alloys are progressively displacing the use of nickel alloys in the rotor blades at the high-pressure end of the compressor. Early engines used aluminium alloys in the manufacture of stator vanes, but it was found that it did not withstand foreign object ingestion damage at all well. Thus steel or nickel-based alloys, which have a high fatigue strength and are less easily cracked or eroded by impact, are now used in the manufacture of stator vanes. Titanium is occasionally used in some engines for the manufacture of the vanes in the early stages of the compressor, but it is not suitable for the production of the smaller vanes further into the engine, where the high temperatures of compression can adversely affect it. Another problem which may occur is that of blade rub, where the rotor blades come into contact with the compressor casing. If blade rub becomes excessive, which might occur through mechanical failure, sufficient heat from friction would then be generated to ignite the titanium. This would, at best, require expensive repairs, or, at worst, cause an airworthiness hazard. The high bypass ratio engine's LP compressor blades, more commonly known as the fan blades, were manufactured in early engines from solid titanium, because titanium combines the properties of strength and lightness. A low blade weight is essential if the fan is to be able to withstand the out-of-balance forces which would occur if a fan blade failed. Despite the enormous strength of titanium, the fan blades had to have a snubber incorporated into their design. A snubber is a support, fitted at mid-span, which prevents aerodynamic instability. Unfortunately, it also adds weight, and particularly when two of them are required, as shown in this picture, they interfere with the supersonic flow characteristics of the air at the extremities of the blade. Experiments with new materials, particularly carbon fibre, were carried out, but its flexibility greatly reduced its effectiveness, and its use has largely been discontinued. The greatest advancement has been achieved by fabricating the blade from a honeycomb core sandwiched between two outer skins of titanium, as is shown here. This method of manufacture gives the fan blade added strength with less weight, enabling the introduction of the wide-chord fan blade, which is portrayed here. The stability of the blade is ensured as a result of its wider chord, and therefore the snubber is no longer necessary. Accumulation of contaminants in both the compressor and the turbine section of the engine reduces the efficiency of the unit. The contaminants in the compressor, which are mostly salt and pollution from industrial areas, reduce the aerodynamic efficiency of the blades, which increases the airflow axial velocity, lowering the angle of attack over the blade, as shown in this diagram. In the turbine, the contamination takes the form of sulfidation, which is a build-up of sulfur deposits from the burning fuel. Sulfidation destroys the aerodynamic shape of the turbine blades and the nozzle guide vanes, and will, over a period of time, erode their surface finish. If the major cause of contamination is salt ingestion, as might be the case with an aircraft which flies for long periods low over the sea, like this US Coast Guard C-130, then a timely rinsing of the compressor with fresh water can avoid use of harsher treatment which otherwise would be required. A compressor rinse can be carried out either while motoring the engine over on the starter or while running the engine at idle speed. This procedure is known as a desalination wash. This picture shows the setup required for washing an engine on another C-130 aircraft. The wastewater in this particular circumstance contains a percentage of cadmium, hence the requirement for a container for the wastewater. If the contamination has reached the stage where a desalination wash is not sufficient, then the application of an emulsion-type surface cleaner may be necessary. The cleaner may be a mixture of kerosene and water, or either solvent-based or aqueous-based cleaner. These are sprayed into the engine intake under the same conditions as the desalination wash. This procedure is known as a performance recovery wash. The turbine can also benefit from a performance recovery wash. For some engines, frequent applications of the emulsion cleaner may justify an extension of their service life. A more vigorous treatment, perhaps more applicable to centrifugal compressor engines, is that of the injection of an abrasive grit into the engine intake while it's running at an idle power setting. The grit takes the form of broken walnut shells. The Americans use the broken stones from apricots. Unfortunately, because the grit is mostly burnt in the combustion chambers, this method does not clean the turbine components as efficiently as does the performance recovery wash. This concludes the lesson on compressors.